Hello, everybody, and welcome to the lecture for Thursday of week 12. So today we're going to talk about Gaussian primes and unique factorization inside of the Gaussian integers. And we're going to explain how that connects back to the problem of finding integers that can be expressed as a sum of two squares. So I want to start out just by recalling the Gaussian integers written z brackets I just means all the numbers, all the complex numbers of the form a plus b times I, where a and b are both integers. So this is a ring. You can add and multiply two such things. And it lives inside the complex numbers, which I can think about as sort of being like r brackets I. The complex numbers are all the numbers of the form a plus b times I, where a and b are real numbers. Okay, so here's a little picture. This sort of shaded light blue is the complex number, is the complex plane. And then these lattice dots here are the Gaussian integers inside of that. So the complex plane is everything, and then the Gaussian integers are just these sort of square lattice points inside of here. And what we saw last week, or sorry, not last week, but what we saw on Tuesday is that for thinking about sums of squares, it's really useful to think about Gaussian integers and their norm. So just recall that the norm of a complex number z is just the product of z and its complex conjugate z bar, which if we write z as a plus bi, then that's just a plus bi times a minus bi. And if you expand that out, you get a squared plus b squared. Another way to think about that geometrically is if I take some complex number, like if this is z up here, then the norm of z is just the distance, the square of the distance from the origin. So I write double bar z for the distance from the origin. I just get this norm is the square of the distance from the origin. So that's another useful way to think about it sometimes. And in particular, it follows from, for example, from this formula, or just from just expanding out, that the norm of the product of two complex numbers is the product of the norms. So, I mean, in general, like if you take an arbitrary complex number, a non-zero complex number, you have sort of a and b are real numbers, and not both of them are zero. So if you take a squared plus b squared, then you get a positive real number. So we can think of the norm as sort of taking in a non-zero complex number and spitting out a positive real number. And then if you sort of restrict to the Gaussian integers inside of the complex numbers, well, then you're looking you're not just getting positive real numbers, but since a and b are integers, then a squared plus b squared is also an integer. So you sort of get, you can think the norm is sort of taking in a Gaussian integer, a non-zero Gaussian integer, and spitting out a positive integer. Okay, so all these properties are sort of very helpful for us. In particular, this multiplicativity property was at the heart of all of the computations we made on Tuesday. We're going to keep building on that. So this, and we can actually just completely reformulate the sum of two squares problem using the Gaussian integers. So the problem we sort of introduced on Tuesday was which positive integers n can be written as n equals a squared plus b squared, where a and b are integers. And now we can just reformulate that by saying which positive integers can be written as the norm of a Gaussian integer z. So when can I get a positive integer as the norm of a Gaussian integer? This is really the same thing because a squared plus b squared is the norm of a plus bi. Okay, so this is really a question about what you can get, what can you get using the norm? And that's nice because that allows us to use the structure of the Gaussian integers to study sums of two squares. And so today what we're going to talk about is unique factorization of primes in the Gaussian integers, and then how through this reformulation, this gives us a complete criterion for when n can be written as a sum of two squares. Okay, so before we get into unique factorization, I want to be a little bit more precise about what I mean by a prime. And I mean, basically, there's a subtlety that already came up in integers that sort of makes things, I guess, even slightly more complicated here. So I want to sort of modify my definitions a bit. So the subtlety that came up when we were talking about integers is like, somehow you could talk about 2 being prime but you could also talk about -2 being a prime. And somehow like you could rewrite, like instead of sort of taking positive prime numbers, you could sort of take the negatives of prime numbers. And you could like rewrite the unique factorization theorem using the negatives of prime numbers. Like somehow for purposes of prime factorization, like 2 and -2 or 3 and -3 are just as good as each other. And so the reason is because 2 and -2 sort of differ from each other by multiplication by -1, and -1 is a unit. So somehow you have two numbers that sort of differ by multiplication by a unit. You sort of can't really tell them apart when it comes to factorization. So we're going to change how we think about things. And we're going to talk about an element being indecomposable instead of prime. So we say a Gaussian integer z is indecomposable if whenever I can write z as the product of alpha and beta, so whenever I can write z as the product of two other Gaussian integers, then one of those two has to be a unit in the Gaussian integers. So this, like if I sort of replace Gaussian integers everywhere with integers, then the indecomposable elements would just be primes and negative of primes. So like both 3 and -3 would be indecomposable. Okay. So let me sort of do an example. I'm going to show you that 11 is indecomposable in zi. So 11, which sort of just means 11 plus 0 times I. So I can sort of, any integer I can sort of think of as being a Gaussian integer. Okay, so well, suppose, so what I need to do, I need to check that if I can write 11 as a product of alpha and beta, then one of them is a unit. So let me just suppose 11 is equal to alpha times beta, for alpha, beta, two Gaussian integers. Well, then I get that the norm of 11, so is equal to the norm of alpha times beta. So and the trick is always going to be to use the norm. Well, what's the norm of 11? Well, it's 11 squared plus 0 squared. So it's just 11 squared. So this is 121. Let me write that as 11 squared. Is the norm of alpha times the norm of beta. Okay. Okay, so now let me sort of break into some cases. I mean, the thing is, this is a fact, like 11 squared is equal to norm of alpha times norm of beta. This is a factorization of 11 squared into two integers, to two positive integers. So sort of possibilities are, for how you could sort of factor this, well, you could have both norm of alpha and norm of beta could be equal to 11. You could have the norm of alpha is equal to 11 squared, the norm of beta is equal to 1. Or you could have the norm of alpha is equal to 1, and the norm of beta is equal to 11 squared. And that's just from unique factorization in integers. I mean, if I write 11 squared as a product of two positive integers, so either they're both 11, or one is 11 squared and the other is 1. So these are the possibilities. Okay, but if alpha is equal to a plus bi, norm of alpha. So in this first possibility, where sort of they're both equal to 11, I might just look at then alpha. Well, if alpha is a plus bi, this is saying that 11 is equal to a squared plus b squared. But this can't happen because this is not possible, because 11 is congruent, is a prime congruent, well, just because 11 is congruent to 3 mod 4. So we already saw last week that you can't get something congruent to 3 mod 4, or not last week, on Tuesday, you can't get something congruent to 3 mod 4 by adding together two squares. So this first case can't happen. But in this second case, so then these other two cases, well, if the norm of beta is equal to 1, that's the same if I sort of write beta is equal to a plus bi, then that means a plus bi times a minus bi is equal to 1. But then that's a unit. So being a unit just means there's some other Gaussian integer I can multiply by to get 1. And so here, if I multiply beta, which is a plus bi times a minus bi, well, I just get the norm, and I get 1. So that's what it means to be a unit. It means there's something else you can multiply to get 1. And so similarly in this last case, that alpha is a unit. So this proves that 11 is indecomposable as a Gaussian integer, because if I can write it as a product of two Gaussian integers, well, I sort of just looked at the possible factorizations for the norm, and I deduced, well, this first one couldn't happen. And then in these other two, I either had the norm of beta is equal to 1 or the norm of alpha is equal to 1. In either case, that gave me either beta was a unit or alpha was a unit. And that's what it meant to be indecomposable. It didn't mean there was no way to write it as a product of two integers. It just meant that if there's a way to write it as a product of two integers, then one of them had to be a unit. Okay. Good. So let me extract a few things, two important parts from that argument. So the first is we saw, let me write this lemma. Let me sort of change how I wrote this lemma a little bit. These things. So the first important thing is we saw that if the norm of z was 1 for some Gaussian integer, then that was a unit. But really sort of it's if and only if. So you can, I'll write that down in a second, but it turns out you can check whether z is a unit just by checking if its norm is equal to 1. And then if you sort of write down the formula for the norm, well, you're going to see that means that z has to be 1 minus 1i or minus I. I'll write that down in a second. And then another thing we saw is that if z is a prime, if the norm of z is prime, then z is indecomposable. I guess, sorry, we didn't see that, but we see this in a very similar way. So let me write this down. Let me write down a proof of this lemma. So for part 1, if the norm of z is equal to 1, z is equal to a plus bi, then 1 is the norm of z, is a plus bi times a minus bi. So z is a unit. Again, I'm just saying being a unit just means you can multiply it by some other Gaussian integer. Since a and b are integers, this is also a Gaussian integer to get 1. So you see this unit. Conversely, if z is a unit, so there exists some other Gaussian integer, let me just call it t in zi, such that s times t is equal to 1, then the norm of s times the norm of t is equal to 1. But that implies that the norm of s and the norm of t are equal to 1. Because the norm is some positive integer. And so if you have a product of positive integers equals 1, then both of those are equal to 1. Okay, so that sort of establishes this first thing. So we can check whether something is a unit in the Gaussian integers just by checking whether its norm is equal to 1. And then if I want to see that that's the same as saying z is 1 minus 1i or minus I, just use that the norm of a plus bi is a squared plus b squared implies sort of either one of a or b is plus or minus 1, the other is 0. So sort of the only way to write a squared plus b squared and get 1 is sort of one of those has to be giving you 1 and the other one has to be giving you 0. Okay, let me sort of make some more room. before I do this example. So I'm going to finish the proof, but I just have to make some more room. So it's the second part. If n of z, if the norm of z is prime, then z is indecomposable. Well, this now follows from the first one. So if norm of z is prime, and z is equal to alpha beta, then just using multiplicative norm, I get sort of norm of alpha. So P is the norm of alpha beta, so the norm of alpha times norm of beta. And then again, using factorization of integers, since P is prime, either the norm of alpha or the norm of beta is 1. So and the other one is just P. And then so by 1, alpha or beta is a unit. Okay, so just to recap, we have a simple way to check using the norm whether something's a unit. And this is an if and only if. And that lets characterize just say the units are 1, -1, I, or minus I. Then in 2, we have a condition that lets us check whether something is indecomposable. It's not an if and only if here, though. So if the norm of z is prime, then z is indecomposable. So that gives us the way we can check. But it's not an if and only if, because for example, I just showed that 11 is indecomposable, but the norm of 11 is 121, which is not prime. So let me add that as a warning. So you can be indecomposable, but norm not prime. So the norm of 11 is 121. Okay, but nonetheless, this is a useful condition that we can use to check when it does hold. Okay, so some more examples. I already showed you that 11 was indecomposable as a Gaussian integer. So let me look at some other integers. And I could also think about 10 instead of it being an integer, the Gaussian integer. But saying someone 10 is already decomposable as an integer. So in particular, it's decomposable as a Gaussian integer. So if you're decomposable as an integer, so if you're not prime, so decomposable or composite as an integer implies decomposable as a Gaussian integer. And if I really want to see this, being decomposable means I can write a product of two things that aren't units. So I just need to check sort of that 5 and 2 are not units. But the norm of 5 is 25 and the norm of 2 is 4. So by sort of this previous lemma, neither of those are units. But what's interesting here is you can have something that sort of is prime as an integer, like 5, but is no longer prime as a Gaussian integer. So prime, so here we can write 5 is 1 plus 2i times 1 minus 2i. So this is sort of equivalent to sort of writing 5 is 2 squared plus 1 squared. So this is prime as an integer. Does not always imply indecomposable as a Gaussian integer. Okay. And similarly, I can write 2 as 1 plus I times 1 minus I. So 2 is also not is also decomposable. So it's not indecomposable. But actually, sort of all these factors here that I wrote, so the 2 factors of 5 and the 2 factors of 2, these are all indecomposable. So if I sort of take the norms, these first one, these have norm 5. These 2 have norm 2. So prime norm implies indecomposable by this previous lemma. So this part 2 of this lemma said that if the norm is prime, then z is indecomposable. So the norm of all these things I wrote down, 1 plus 2i, 1 minus 2i, these I both have norm 5, that's prime, so they're indecomposable. 1 plus I and 1 minus I both have norm 2, that's prime, so they're indecomposable. Okay. And so if I sort of trace through all of these, I first wrote 10 is 5 times 2, so 10 was decomposable. But I notice this isn't the prime factorization anymore when I think it was a Gaussian integer. I mean, somehow, because 5 and 2 sort of both break down further. 5 breaks down as 1 plus 2i times 1 minus 2i, and 2 breaks down as 1 plus I times 1 minus I. As a Gaussian integer, I can factor 10 as sort of 1 plus 2i times 1 minus 2i, that gives me 5, times 1 plus I times 1 minus I. Okay, let me just sort of observe one other interesting thing that's happening here. Going back now to this sort of difference between indecomposables and primes, and sort of like the distinction between like minus a prime number and plus a prime number. If I look at this factors 1 plus I and 1 minus I, actually sort of 1 plus I and 1 minus I, these differ from each other by multiplication by a unit. So 1 minus I is minus I times 1 plus I. So somehow like I should really think of these as giving me the same prime number. Just like I think of sort of like in integers like 3 and minus 3 sort of would give me the same prime number in some sense. Like they sort of apply equally well in unique factorization. If I have, since I can write 1 minus I as minus I times 1 plus I, I could sort of rewrite this factorization of 10 instead by saying 10 is the unit minus I. This is the unit. Times this indecomposable and this indecomposable. So these two don't differ by multiplication by a unit. And you can just check all 4 units and see you don't get sort of, you can't go from here to here. So these two are sort of somehow really different primes. And then now I can just write 1 plus I squared. So somehow this is sort of like the prime factorization of 10. In fact, so I'll usually write it a little bit different this, but okay, this is sort of one way you can think about being the prime factorization of 10 as a Gaussian integer. Okay, so sort of to handle this ambiguity between like plus a prime and minus a prime, or sort of more generally like two sort of numbers, two indecomposables differing by multiplication by a unit, let me define a Gaussian prime. Instead of sort of being a single numbers, it'll just be sort of a collection, a set of indecomposables, such that any two of them differ by multiplication by a unit. So any Gaussian prime sort of consists of 4 indecomposables, where I can get from one to the other by multiplying by a unit. This would be like, instead, if I define a prime number in the integers to be sort of a positive prime and its negative. Like if I just sort of thought of those as sort of being a set together. So by writing the Gaussian integers, well, I told you 11 was indecomposable. If I multiply indecomposable by a unit, it's pretty clear that what I get is indecomposable. It's a good exercise to check if that's not clear to you. And so I get a prime, which is taking 11, looking at all of its multiples by units. The units are minus 1, so that gives me minus 11, I, so that gives me 11 times I, and minus I, so that gives me minus 11 times I. If I look at this other prime right down, so 1 plus 2i, I saw that was prime because its norm was 5, which was prime. Then if I take minus that, I get minus 1 minus 2i. If I get to take I times that, I get minus 2 plus I. If I take minus I times it, I get 2 minus I. And then you see this is really different than what I get if I start with 1 minus 2i, which was sort of this other prime appearing in the factorization of 5. This other indecomposable appearing in the factorization of 5. I get 1 minus 2i, minus 1 plus 2i, 2 plus I, and minus 2 minus I. And so these sort of don't overlap at all. So these are really 2 different primes. Whereas if I sort of do it for this prime 1 plus I appearing in the factorization of 2, I get 1 plus I, minus 1 minus I, minus 1 plus I, and 1 minus I. So in particular, sort of 1 minus I and 1 plus I differ by multiplication by minus I. So some of the 2 different indecomposables, but they sort of give you the same prime. Okay, so once we sort of have sorted this thing out with the units and sort of indecomposables, though, we really can sort of get a prime factorization with a prime factorization theorem in the Gaussian integers. And moreover, we can sort of understand exactly sort of what the primes are. So this theorem states that. So the first part tells you sort of what are the primes. And so any Gaussian prime contains exactly one indecomposable of the form, well, it's either just 1 plus I. So this is sort of the prime that divides 2. Or it could be A plus BI or A minus BI, where A is greater than B are positive integers with A squared plus B squared, an integer prime that's congruent to 1 mod 4. So this is like this 1 plus 2I and 1 minus 2I. Okay, so here we're looking at A plus BI or A minus BI, where A is greater than B. So here, so the distinguished representative would be 2 plus I. And then here, the distinguished representative would be 2 minus I. Okay. And so somehow you can see that sort of these decomposables are sort of conjugates of each other. One's complex conjugate of the other. And just like we had sort of up here between sort of 2 plus I and 2 minus I. Or the last possibility is just if P is an integer prime, this can go to 3 mod 4. And so the argument for why this thing is prime is just like how we argued that 11 is prime. The same argument works for any integer prime that's congruent to 3 mod 4. Okay, so these are all the Gaussian primes. So another way to think of this is literally Gaussian primes are sort of attached to integer primes. So if you have an integer prime that's congruent to 3 mod 4, then that sort of gives you, it stays prime in the Gaussian integers. But if you're congruent to 1 mod 4, then you sort of split into 2 different primes. You sort of factors A plus BI times A minus BI, where A squared plus B squared is equal to P. So that uses what we did on Tuesday to see that you can always do that. And then if you sort of look at 2, then sort of 2 is no longer prime, but sort of just it factors as sort of like 1 plus I squared times a unit. So sort of there's just 1 prime sort of corresponding to 2, but sort of somehow smaller than 2. Okay, so these are sort of the primes. And then the statement is that any Gaussian integer Z has a unique factorization. Sort of, well, you can write it as a product of these indecomposables, where you sort of take them in this specific form written here. So each of these gamma i's are sort of indecomposables as in one of this form, sort of unique up to reordering. And then you have to sort of write also, you have some unit out front. So just like sort of an integer is sort of plus or minus a product of primes. Here, a Gaussian integer is some unit times a product of primes, or product of indecomposables of this sort of specific form. And this, well, any unit is 1, minus 1, I, or minus I. And so those can all, and you can also think those of you being just the powers of I. And so then the power of I that appears is sort of, well, corresponds to some integer in Z mod 4Z. Okay, so this is sort of how you can say unique factorization in Gaussian integers. Let me just state as a corollary, we finally get our result about sums of squares. So the statement about sums of squares is that a positive integer n is a sum of 2 squares, if and only if n is a product of integer primes. If and only if when you write its prime factorization as an integer, then sort of the exponents appearing are even when the prime is congruent to 3 mod 4. I mean, some of this sort of correspond, and we already knew that sort of if you had a prime congruent to 3 mod 4, you couldn't write it as a square, as a sum of 2 squares. But so if you square it, then it's already a square of an integer. Like, so it's like p squared is p squared plus 0 squared. So when you square something, you always get a sum of 2 squares. And somehow this is the only issue. Like once you sort of have handled, like you have to do that. Once you've done that, like that completely determines everything. So that's the idea here. But to sort of see, like to prove this corollary, what you have to do is you just use the theorem, which sort of says what the Gaussian integers are and what the Gaussian primes are. and then you just sort of take unique factorization of Gaussian integers. And if you take the norm, then you'll see like what you have to get. So if you take the norm of this, you get 2. So you're sort of allowed to have any number of powers of 2. You take the norm of something like this or this, you get sort of just the prime congruent to 1 mod 4. So those are fine if they appear. But if you take the norm of this, you get sort of p squared. So sort of anytime you have one of these indecomposables, you're getting when you take the norm, you're getting a square of a prime congruent to 3 mod 4. Okay, but once you have that and the results from last time, then we're good, and you really get this characterization of the sums of 2 squares. Okay, so the only question is sort of how do you prove this theorem? We've already sort of somehow done a lot of it. So the arguments above, like, and so I gave them the special cases, but they really showed, and the arguments above, like for 1 plus 2i, it's like I said, that was prime because its norm is prime, and so that argument applies like always in this case to show these things are prime, or sorry, 1 plus 2i that I showed that was indecomposable. I showed its norm was prime, like that always applies. So using your indecomposable if the norm is prime sort of tells you that these guys are prime, are indecomposable. And then the argument I gave to show 11 was indecomposable shows that actually any integer congruent to 3 mod 4 is indecomposable. Okay, so that sort of gives you part of the theorem and says that at least all of these are really indecomposable. After you have that, sort of to show that those are the only indecomposables, you sort of need the second part. So you need to have unique factorization and like a Euclidean algorithm in GCD, and then you can sort of show that these are really the only primes. Yeah, and some of the key things showing that it's only primes is really sort of having a Euclidean algorithm. And the key thing for showing you have unique factorizations is also having a Euclidean algorithm. And there's just like when we showed unique factorization for integers, the key thing was to have a Euclidean algorithm. So that's the ingredient that's left, is we need to have a Euclidean algorithm for Gaussian integers that lets us compute their GCDs. And well, we do. And turns out you have a Euclidean algorithm that's exactly like the Euclidean algorithm for integers. And you just have to use the following basic fact about division, which says if alpha and beta are Gaussian integers, then you can always write beta as q times alpha plus r, where the norm of r is less than equal to the norm of a, or sorry, the norm of alpha over 2. So this looks just like division for integers. We're just sort of measuring how, but like to measure how big the remainder is and say the remainder is smaller than alpha, like sort of we're using the norm to say it. And then it's somehow even better because we get less than the norm of alpha over 2, or less than equal to the norm of alpha over 2. So not just less than the norm of alpha. So it's actually sort of even a little bit stronger in some sense. And so, I mean, to see that you can do this, I just have to explain how do you construct this quotient q, and then you can sort of check for yourselves that the remainder, when you sort of construct q this way, really will be smaller, or you can just sort of take it on faith and see that it works out in examples. Well, it's pretty simple. And so to do this, what I do is I just divide beta by alpha inside the complex numbers. There's a simple formula for that. That's just beta times alpha bar over the norm of alpha. That gives me some complex number x plus yi. And then, but these x and y, then these are sort of going to be rational numbers if I start with Gaussian integers. And so to get q, then I just round these rational numbers to the nearest integers. Okay, and so you can check this is always sort of, okay, that gives you q, and then once you have q, you can compute the remainder. And so this is sort of just like the division algorithm. And if I divide two integers, I can sort of divide them as rational numbers and then sort of just round to the nearest integer to get q, and more or less. Good. So once I have this, I can sort of do the Euclidean algorithm to compute GCDs. So let me just sort of show you an example quickly, and you can go through it more slowly on your own time if you'd like. So I want to compute the GCD of 11 plus I and 61. Well, I need to write 61 as sort of Q1 times 11 plus I plus R1. So I sort of do this thing I described above. If I want to compute Q1, I divide 61 by 11 plus I in the complex numbers. So I get that 61 times 11 minus I over 122, which is the norm of 11 minus I, which is 11 over 2. So 61 over 122 is a half, minus I over 2. And then, so this is X. So here my X is 11 over 2. And then my Y is minus a half. And so I round that up to get Q is equal to 6. So sort of 11 over 2 is 5.5. So we always round 0.5 up. So that goes to 6. So minus a half is minus 0.5. And so you always, with negative numbers, you still round up. So sort of minus 0.5 doesn't become round to minus 1, it rounds to 0. So minus 0.5 is 0. So you just have to be a little bit careful always about negative. It's unambiguous how you round a number, sort of if it's not sort of a multiple of a half, but sort of negative 0.5, like it's just as close to sort of negative 1 as to 0, but you always round up. So negative 0.5, you always round up sort of 0.5. So when you do that negative number, that means negative 0.5 goes to 0. Okay, so that's why we just get 6 here. This becomes rounds to 0. Okay, and so then, well, okay, then I get 61 is 6 times 11 plus I. And if I just expand that out, then I can subtract off and I see the remainder has to be minus 5. The remainder is minus 5 minus 6I. So 66 plus 6I, to get to 61 from that, I have to subtract 5 and then also subtract 6I. So this is the remainder. Okay, and then I sort of keep on doing my Euclidean algorithm for now. So now I sort of divide 11 plus I by the remainder. Okay, and I do the same thing. And I end up getting minus 1 plus I. And I really get it on the nose, like these are already integers. So I don't need to do any rounding. And I really get 11 plus I is minus 1 plus I times minus 5 minus 6I with no remainder. Okay, and the GCD is sort of the last thing when we didn't have a remainder. So I get that minus 5 minus 6I is the GCD of 11 plus I and 61. In note here, 11 squared plus 1 squared, so the norm of 11 plus I is 2 times 61. And we already saw this in an example using descent to sort of write 61 as a sum of 2 primes. And indeed, or as a sum of 2 squares. The norm of minus 5 minus 6I is minus 5 squared plus minus 6 squared is 61. So somehow actually, okay, so basically what happens when you do this Euclidean algorithm is exactly the same thing that happens when you do descent. Sort of if you're sort of set it up, if you're in this kind of situation. I mean, like here, like this minus 1 plus I, or sort of maybe something very close related to that, also showed up when we did this example in class on Tuesday. Okay, so somehow you can rephrase descent as sort of a special case, this descent argument for expressing a prime as a sum of 2 squares as sort of a special case of the Euclidean algorithm in the Gaussian integers, which is sort of a nice way to think about it. But we'll talk more about that in class on Thursday. I will see you there, and thank you.